Okay, so this is 2.5 out of Griffiths, which is to find the electric field a distance z above the center of a circular loop of radius r that carries uniform charge density, uniform line charge lambda. So what we have here is a circle, and we want to find the E field some point z above the center. Okay? Well, first off, hopefully you can see by the symmetry of the circle, the E field's only going to be in the z direction. And this is similar with a lot of problems we've done with continuous charge distributions, like the previous video. You might have a charge density, you take a bit here, or a bit here, or a bit here, or a bit here, or wherever you want to take it. Hopefully you can see that there's an opposite side that will cancel in your, we can call it x direction. So horizontally, you could think in the x and y direction, they're always going to be canceled. And the only where they're not going to cancel is in the z direction. So just as an example, let's say you had a chunk right here. Maybe you had a chunk right here. That's not a good arrow. You have these two E fields. And this side and this side, even though it's not perfectly drawn, is equal and opposite. Whereas this side and this side actually add together in the z direction. And you can go all around the circle, you'll find that to be true. So hopefully that makes sense. So the first thing I want to note is by symmetry, only the z direction makes it. Everything else will get canceled. Okay. Now I want to look a little bit at our circle here. Let's say this is r and this is r. They're both going to be a radius r from the center. And this is a small bit of angle d theta. And we'll call this a small bit of arc length ds. And if you remember from, I think, trig, ds is going to be equal to just r d theta. So we're going to need that. Okay? Cool. So our E field, we're going to need to find some information. Let me do this in black. To start, we'll need our dq, just like before. dq is going to be lambda times ds, because lambda has units of charge per length, and ds is a bit of length. But we just found out what ds is. ds is r d theta, and we'll call these capital R's. I think that's what the book does, or with the, no, they're little r's. So we'll actually keep them little r's, no big r's. Okay. So that's lambda, or that's our dq. Script r, that's the distance from where we're interested. That's just basically your separation vector. So that's going to be r squared plus z squared square root. You can see that by the symmetry. You could also have done vector r is z k hat, r prime is r, you can just call it r hat. So then script r is going to be r minus r prime. But that's not even necessary. We just are looking for this distance here. This is our script r. And if we square both sides, we get r squared plus z squared. Okay? So our E field is equal to 1 over 4 pi epsilon naught. That's our constant. Integrating, we'll come back to that. Our dq over r squared. And then what we're going to do is we're going to multiply by cosine theta, and then we have the d theta here. Why are we multiplying by cosine theta? Well, this is to get our direction. So we just want the x component here. We just want that part. Yeah. So we just want that part there. So if we look at the triangle down here, let's call this theta. Oops. We'll call this theta. So we want that part there. So cosine theta is going to be equal to your adjacent over your hypotenuse. And then we can just plug that in. So again, multiplying by the cosine theta is just basically turning our E field in just the k hat direction. That's what's happening when we're multiplying by cosine theta. And then we're going to replace cosine theta with that. And then our bounds of integration will be 0 to 2 pi r. In other words, the entire circumference. I guess I can put the constants. It doesn't really matter. Times lambda over. Let's see. We're going to have r squared plus z squared to the 3/2 times z d theta. Well, now everything but the d theta is a constant. So you could think of factoring that out. You'll be left with just theta. So our E field, and remember the x direction is all we want here because that is our E field, is lambda z r squared plus z squared to the 3/2. These are all just constants. And then when you're left with just the integral of d theta, it's theta, and then you integrate with your bounds, and you'll just have 2 pi r. This is your E field. So hopefully that helps somebody. It helped me, so I guess that's